to present on my research work. Alexander Nyako, currently I'm a student. I'm having my dissertation on FTI, CNRS profiles of bioproduction analysis of risk components and environment and nature conditions. My supervisors are Professor Nicholas, Dr. Nicholas, and CNRS. So I'll give the background of the given objectives, methodology, results, and discussion, conclusion, and references. Ever since the question in 1879, I introduced the Leonardo cocoa products in Ghana here and established a cocoa farm in the eastern region of the Mountain. Now, Ghana has actually been exploiting cocoa, and hence currently Ghana is even the second largest producer of cocoa. Now, cocoa has very important byproducts. You see, we have the cocoa products, the mucilage and the shell. But it could be interesting to know that the cocoa products constitutes about 76% of the cocoa crop. Now, Mendoza et al. In 2021 published that in 2017, out of the world estimation of cocoa production, that is 1.2 million tons, we had 85% going out as cocoa industrial waste, i.e. cocoa products. This means that this biomass source, this waste biomass source, is being produced in large quantity. However, it has actually been underexploited. Now, various researchers have said that when we focus on this particular biomass waste, it could in fact become a very good alternate fossil fuel source, and also it could be a very good alternate fossil fuel and green platform chemicals. Now, Scientifique in 2018 had reported that indeed there are 20 varieties of cocoa. However, 95% that are the top three, which are we have the Trinitario, Criollo, and the Forastero. Now, the Criollo breed is a rare breed. The Trinitario breed is actually a hybrid breed. And the Forastero is the commonest in Africa, that is the C, as you can see from this particular slide. Now, cocoa products has various compositions. So, it's ligneous and basic. This means that it comprises of cellulose, semicellulose, lignite, minerals, organic fibers. And then also, in terms of structure, we have the apical, mesocal, skeletal pack, and then endocal. You see, there are various conversion technologies. Now, we have biological and thermochemical. However, under thermochemical, we have pyrolysis, compaction, and gasification. Now, according to so many researchers, even from Bridgewater 2011, pyrolysis conversion technologies have actually demonstrated that if you want to actually achieve optimum bioeconomy, that's the way to. Now, FTIR and GCME. So when we talk about FTIR, simply we are talking about Fourier transform infrared spectroscopy. Now, it's a powerful analytical technique which is used to obtain the infrared spectrum of absorption or emission of various materials. And GCMS is actually gas chromatography mass spectrometry. You see, it's a sophisticated analytical technique because it combines two powerful methods. That is the gas chromatography and the mass spectrometry. So it allows for the separation, identification, and quantification of compounds. This is the problem statement. You see, due to poor agricultural waste management of cocoa products, the image you see on B is how our farmers just leave the cocoa products on our farmland. Now, this actually brings an inoculum which brings about, black pod rot infections. And this leads to an annual crop loss of about 30 to 90% for individual farmers. In fact, there is little research into the product distribution of biomass from waste cocoa products at high temperatures. And so we seek to contribute to existing knowledge. The aim is simple, to study the FTIR DCMS profile of biomass produced from pyrolysis of waste cocoa products under varying temperature conditions. And our objectives: 1, we are going to characterize waste cocoa products. 2, we are going to analyze and characterize biomass produced from pyrolysis experiments. The methodology, so we were able to obtain fresh cocoa products from the KNUST cocoa plantation. We treat it by sun drying it for 2 to 3 weeks, and then we crush these cocoa products. We fetch samples of the crushed cocoa products for approximate and ultimate analysis. Thereby, we prepare it and then we sieve it. Then the remaining crushed ones are what we are going to use for our analysis experiment. So talking about the characterization of the cocoa products, there is ultimate and ultimate. So we determine what shall contain volatile matter, ash content, and phase carbon using the standard ISO 562/1974. And also under the determination of ultimate analysis, we check for carbon, hydrogen, sulfur, nitrogen, oxygen, and using the source Nelson data 1982 and Hins DL 1984. In fact, it's important to do this characterization because you have to know what you are going to get. You don't just set fire and start doing something. That's why we are doing this. Now, this is basically the schematic model of the reactor that we set out for the pyrolysis experiment. Now, we did also, after doing this pyrolysis, we were able to obtain our oil. Recognize that we are heating at 5 different temperature ranges: 300, 400, 500, 600, and 700. Now, what we are going to do is that after getting our oil, we are going to perform physical chemical analysis on the bio oil. This is the standard ISO 3104. Now, what this means is we are going to check for density, viscosity, and pH. And then also we did FCR analysis and then GCMS analysis. These were the results. This work is simply my results. And as you can see, for our moisture value, we have low amount of moisture, which was very, very good. Now, ash is actually non-combustible. We have low amount, which is also good. There were high volatile matter, which simply means that we are going to actually achieve optimal amount of bio oil. Then we have face carbon content. Now, basically, these values were consistent with that of reported literature works, and that's why we're doing this comparison. Similar with the ultimate analysis. Now, this was the physical chemical analysis. As you can see, as temperature increases, the pH increases. However, the pH is actually acidic. And then this further confirmed after we did the FTIR and then the GCRS, so we saw carboxylic acid, etc. Now, we saw viscosity actually increases as temperature increases. When you watch the density, it's supposed to actually increase as temperature increases. However, at 400, there was a bit of discrepancies. It is very simple because in performing the density analysis, we are pouring the oil into a kilometer. There are lamps in it, and you know density is mass over volume, so there were a little discrepancy over there. Now, this was our oil, and these were our biochar samples. So now, product distribution analysis. So as you can see, 300, 400, 500, 600. I'm going to explain this using this graph. Now, the red plot is for the biochar samples. As you can see, as temperature increases, our biochar amount decreases. Now, the black is for the gas samples. As temperature increases, you can see that the gas is increasing. However, with the blue, which is the bio oil, you can see that optimum amount of bio oil was achieved at the temperature level of 500 degrees Celsius. So, FTR analysis. So, yes, we did analysis for the raw cocoa waters. We also did analysis for the bio oil samples. In fact, we went ahead to do analysis for the biochar. But I realized that with the biochar, wait, let me explain this. Now, with the FTR, we use the peak. So, the moment the Peckinpah instrument identifies the peak, it gives us the wave number, right? So, with the wave number, we did for the raw cocoa waters, we realized that there were phenols and alcohol compound in it. Now, this is to actually detect the functional groups. We have alkane groups, we also have carbonyl groups, IE, ketones, aldehydes, and then there were also ethyl groups. Now, to give basically the class of compounds. For the oil, you can see that the OH is very predominant, right? And then you can also see that there is an alkyne group, and there is also the carbonyl group, alkene group, and then there is alkane group. Now, when you from the rest of the temperature release and you superimpose them, you can see similar traits, which means that when you consider all these oils, they possess all these functional groups. This is basically a sample of that. So we did GCMS to now know the sort of compounds that are in this oil that we have achieved from paralyzing the waste cocoa products, the way that the farmers are getting disposed of the farm. Now, at 300 degrees, we were able to discover about 74 compounds. At 400, 500, 600, 700, we saw 15 compounds. Now, recognize that these compounds are actually significant in number. So in order to perform a very good analysis, out of the 74, we select the top 15 so that we can compare to 400, 500, 600, 700 and look at the behavior of these chemical compounds. So over here, when we did our comparison, we realized that as temperature increases, some of these compounds break down completely. Some break down to form new compounds. And so when you do all the estimation, we have 30 compounds from 300 to 500. So basically, when you look at this particular case, there is a red line here. You have 300, 400, 500, 600. What we discovered was that the toxic serintol, which is actually the toxic phenol component, guaiacol, which is also the toxic phenol component. Now, these components actually emanate from lignin decomposition, and they were actually repeating throughout. We talk about they are thermally stable. Now, I would have loved to talk about everything, but then due to time. But anyway, when you look at the 300 degrees, phosphoric acid was actually the highest. When temperature continues from 400, 500, 600, you can see that acid and ester compounds such as 3-pro-panelic acid, 2-methyl-cyanide are repeating the other complex compounds. Now let's continue. So from 11 to 20, when you look at 400, I'm holding some of the numbers. Now these are actually the new compounds that compare. And I've actually done a bar graph to explain this. What we did was we grouped all these chemicals into 7 major components. So we have phenols, alcohols, ketones, furans, guaiacols, and serinols, acid and esters, and then miscellaneous compounds. Where the miscellaneous compounds are complex compounds. This was the analysis. Now, the deep blue represents phenols. Phenols are coming from lignin decomposition. The light blue are acid and esters. The red is actually miscellaneous compounds. Now there's a certain thing orange, which is for phenols. Then there is a yellow one, which is for ketones. What you realize is that when you get to 400, the deep blue increases together with the green. Now the deep blue, I said that is coming out from liquid decomposition. So from this experiment, we realize that at 400 degrees, the liquid decomposition was very sharp. We talked about that. So at 400 degrees, we have liquid actually breaking down. And of course, there is the polymerization reaction happening. Simply breaking down of polymers into oligomers and monomers, right? So, and then also realize that now, as temperature increases, alcohols, furans, which are actually coming out from cellulose and hemicellulose decomposition, they're around 300 and 400. And of course, as temperature increases, we can still see more of these phenolic compounds and toxic phenolic compounds being generated together with other various compounds. This was actually a bit different from banana paralysis. Those that are done by banana paralysis, as temperature increases, the acid and esters decreases. This was an interesting revelation. The new compounds, at 700, there was particle production in high amounts, 23.08%. This was striking something that surprised us, right? Now, also at 400, when you look at this, look at phenol. Phenol was very, very high in value. And as I said, liquid decomposition basically just breaking down. Now, these are some of the structures we identified. And I just selected some few. We have structures for all the chemical compounds. These are just some few ones, right? So you can see phosphoric acid, you can see the acid and ester compound. Then you can see the aspidous palladium compound, a very interesting compound that actually appeared in high amount as temperature increases. Upon further research, we realized that this particular compound will be used in treating cancer. Aspidous palladium, a very interesting compound. At 400, there was phenol, then toxic phenol. Then look at succinic acid, an acid and ester compound. Look at that structure, very interesting. What we realized was that the ester derivative from the succinic acid would actually be used in making flavors and fragrance. And so when we saw these two, we realized that there was another interesting chemical compound discovered in this for example. At 500, you can see cyclization reaction happening. At 600, there is isonicotinic acid, a very interesting structure over there. Now, isonicotinic acid is also used in treating tuberculosis. It can be used as an anti-tuberculosis drug. Another interesting one. Then there were bicyclic compounds, as you can see. A very interesting complex compound. And then, of course, at 700, there was statical, and then another interesting one, fluoroatropine. So, significance of the compound. So, with statical, they will be used as precursors to neurotransmitters like dopamine. Then they also have antioxidant properties for cosmetic and polymer products. Now, with fluoroatropine, it can be used as an antidote for poison, and also for chemical synthesis. And then lastly, as I said, the aspidous palladium compound is used in treating cancer and treating inflammatory diseases. So in summary, we've realized that temperature indeed has an effect on yield and composition of bio-oil. We've also achieved that optimal temperature for bio-oil yield is around 500 degrees Celsius. And of course, bio-oil as a periodic product from waste co-products consists of various specialty chemicals. We are also able to achieve biochar, which also is also an important bio that achieves several applications. Then lastly, the co-products is indeed a valuable agricultural waste source. So wait, acknowledgement. I'd like to sincerely grateful to the directors of the University Recherche for this privilege. Also grateful for the necessary support, guidance, and mentorship of the supervisors, the lab technicians, and big appreciation to the Department of Chemical Engineering for providing the opportunity to pursue my academics from the graduate to the graduate. Then lastly, a big thank you to each and everyone for your audience.